Hi there. This is a reliability analysis of an on-site process plant using address. So you can see here I made a reliability block diagram whether you have the main system here and a backup system. So the one which shown here is in blue is the reliability of the main system, and the backup system shown reliability of the backup system is shown here. Now this is they are parallel, means this one in operation, and when this fails backup system comes into operation. The total reliability of the system is calculated using this formula. Now we're going to study what is inside this main system, which determines the reliability of the system. So I have conducted two RAM study. RAM means reliability, availability and maintainability study. RAM study 1, you can see here it's a configuration 1. It shows a subsystem of the main system. So you have these are the components inside the main system. You have a unit 1A, unit 1B, unit 2, unit 3, unit 4, and the reliabilities of this are estimated. These are estimated values. It's 0.95 for unit 1A, 0.95 for unit 1B. Since they are parallel, the resulting reliability is 0.9975. It's calculated using this formula. So reliability of unit 3 is 0.93. Reliability of unit 3 is 0.98. It's an estimated value. And unit 4 is 0.99. It's depending on the characteristics of this unit. So I'm not going deep inside each of these units, but giving you a fairly an average value of reliability we can estimate for each of these units. So the main system reliability works out around 0.9 using this formula. Just we multiply all the reliabilities in series and get this value because they are in series. So we're going to get the reliability of the parallel system here and multiply with the reliability of unit 3, unit 3, unit 2, unit 3 and unit 4 and get the main reliability as 0.9. This value can be taken here and calculate for the total system. Similarly, for RAM2, what we have done is configuration change. We add another one more parallel system to unit 2A and 2B. So the reliability of system 1A and B is 0.9975 since they already in parallel. Similarly, for unit 2A and 2B, the reliability is 0.9951, which is increased. If you can compare with the previous one, it's about 0.93 estimate to 0.9951, because you're going to add redundancy to the system. The unit 3 reliability is 0.997, unit 4 0.998. The total reliability works out around 0.99. So it's multiplication of reliability R1AB, R2AB, R3, R4. You can see in this formula. So what we are doing in the configuration 1 is we're going to do the RAM study, that is reliability, availability, maintainability study 1. So I have estimated the mean time between failures in hours, and they are indicated for unit 1 AB, unit 2, unit 3 and unit 4. These are based on experience, empirical results we obtain from observing the failure, mean time between failure or mean time to failure. I assume they were almost the same. And then the lambda is nothing but the inverse of mean time to value, and then mean time to repair is also an estimated based on the experience observations we have from the field. So it's been estimated here. I'll come to what it's indicated in blue later on. Mu is again the inverse of MTTR, and alpha is nothing but the ratio of MTTR divided by MTBF. And availability is nothing, the formula of availability is 1 by 1 plus alpha. Availability and reliability is, availability factors the maintainability in reliability, so you get a total picture of the availability of the units. And for finding out the return on investment, availability is an important factor. Reliability is a design factor. Availability is the actual availability of the unit, which factors the maintainability. So availability is an important factor when it comes to operation of the unit. So you have for the main system, from based on what we have, the information for each of the unit, main system, you get the average mean time between failure. It's about 245.86 hours. They can be changed, but I'll come to that later. So lambda is summed up, it's 0.00407, it's summation of all the lambdas we have in series, and mean time to failure is calculated using this formula, and alpha is again summed up, and the availability of the total unit is calculated using this formula. Now what we're doing here is we're defining a distribution for mean time between failure and mean time to repair. So we know what's the mean time between failure, and I'm defining a distribution in order to carry out the Monte Carlo analysis. The mean time between failure for unit 1 AB, and I go to the address, I click on define distribution, and I've chosen normal, because you click on this, you can select the distribution you want and set the mean I've selected is 720 hours, standard deviation of 72, and I've taken the confidence level within the 90%, and 5% on the left side and 5% on the right side I'm leaving. So it's fairly, I'm assuming it's a normal distribution, and I'd say OK. Similarly, I define a normal distribution for unit 2, unit 3 and unit 4, as you can see here. And for a mean time to failure, I define a distribution as viable with alpha is equal to 2, beta is equal to 3. Beta is equal to 3 is fairly and close to normal distribution, but I have control over the distribution. That's why I'm choosing viable. And the shift I've taken 15, so the average is around 17, but I can fall in this range with a maximum peak around 17 hours to repair unit 1 AB, and I've taken a viable distribution. As you can see, the mean is 17.657, the mode is 17.12, the median is 17.49, and standard deviation about 1.38. There's a skewness about 0.63, and the curvature is 3.24. That depends on the beta. Similarly, I've chosen viable for unit 2, viable for unit 3, and unit 4 I've chosen a viable with standard parameters I've shown here. And then this red symbol shows the output. So I have to add an output by clicking on this and then get this output. Now I wanted to simulate it. So just if you when you roll the dice, as you can see a symbol here, the values keeps changing. As you can see here, the values keep changing. And I start the simulation. So you can see that from the histogram here, the possible availability of the total system based on the present iteration. It's around 0.91. Similarly, for RAM to study, I've made a table here where you have the MTB, lambda, MTTR, mu, alpha, and availability. That is maintenance time to ratio. Alpha is maintenance time ratio. And I've chosen the unit A, B values of 70, but the mean time to repair is 7 because they are in parallel. Similarly, the mean time to repair for unit 2 is also reduced to 10. I've chosen a distribution which is gamma, but because I'm fairly optimistic, the distribution will fall within this range. So it means a little bit repair at much shorter time than what has been estimated. Similarly, for unit 2, I've chosen the distributions gamma, so I'm fairly confident that I'm able to pair in a fairly short time. Similarly, I've made a defined distribution for unit 3 and unit 4, and I use the die, values keeps changing, and I have the output which is 0.979. Let us simulate. I'm taking a 500 iteration, I'm doing one simulation, and I'll start it here. So value is about 0.9656, and you follow the histograms like this. So it's got a mean value of 0.967, the mode is 0.969, the minimum is 0.919, the maximum is 0.985. And I'm go back to the main. I've defined a distribution for our main and our backup. Our main input comes from what we have done these two study. So I've chosen a distribution which is PERT, and I'm fairly confident to have it in the range 0.8 to 0.9, as you can see here, and the maximum 0.98, and the mean of 0.73, and mode of 0.8. This is just for simulation. I've chosen these values, but I should pick up values from here. Well, for the time being, let us take what we have so that we can do more realistic analysis of the R total. R total is calculated using this formula, and I start the simulation. It falls in the range of 0.91. That's a value we generally in practice we get. So in order to generate report, we click on export Excel report, and I click the quick report, input result summary, output result summary, and also I have defined the inputs and outputs, the model definitions. So I say OK. The report Actress generates a report. As you can see, this is a risk output report for R total, and the value I'm using a 500 iteration. The results I'm getting is upper is 0.97, the lower is 0.817, and for backup 0.83 is the lower, the upper is 0.97. As you can see in this tornado graph. and this gives the cumulative safety and the range of between 0.76 and 0.93. It's about 90%. This is for the next output, where this output report A for main system. So you have the unit to the mean time between failures, the range is knows. Similarly, in mean time to repair is for unit 2 is also has got a range. The rest is fairly in control. Similarly, for output for the main system, where we have the, as you can see here, mean time to repair for unit 2A and B is improved, but you still have the range, and unit 1 you still have a range. The tornado graph clearly indicates where do we stand after the modification. The input results, what are the kind of distributions we have chosen, is clearly shown here, and output results shows for the total and for the main system with RAM study 1, RAM study 2. And the details are given here, and the model inputs are also given here, and model outputs also given here. Well, this gives a clear idea about let's save it. This gives an idea of how the Monte Carlo simulation can be applied for reliability systems such as this. And in order to decide which distribution to choose and how to analyze more accurately, there are several resources available, like the one this particular book by ReliSoft gives a detailed data about live data analysis. It's reference to, and you get to see the distribution, what kind of distribution to be used for what particular application or what particular reliability analysis. All the informations are given here, so it gives understanding of when to use log normal, when to use Gaussian, and how the estimates probability plottings, how are they done. And similarly, a lot of resources available on the internet. We have bible.com, Bible model parameters, and there is a reliability engineering resource websites which gives in detail on selection of the distribution for this analysis. If you have any questions, you can email it to me at satyanarayan.apia@gmail.com. Thank you.